So, today's edition of ENGR 425, I think it's -R, we're going to be wrapping up normal shocks and kind of moving into oblique shocks, also otherwise known as oblique shocks. So, last time we wrapped up, I believe, with these guys. If you look at the slides, we got to our normal shock relations. So if I know the Mach number upstream of the shock, I can tell you. If I know what the flow is upstream of the shock, I can tell you pretty much anything you want to know downstream of the shock. That's kind of what the upshot of that was. Conveniently, so one. Not conveniently, just something that's kind of cool. So we derived all these things from just thermo, pretty much, and conservation of energy, mass, and momentum. They actually hold true. Like if you go and do flight tests, these things actually work. It's really kind of cool. Even with the assumptions that we've thrown at it. The relationships are pretty darn good in terms of what they mean. So here's a little chart. I'll kind of blow it up here a bit. It kind of talks about that a bit. So we had seen this curve for Mach number. Note that the arrows point to which axis you should be looking at in order to reference a given curve. So we had looked at the curve for Mach number before. We said that across a normal shock, Mach number will always decrease. Not only that, Mach number after a normal shock will always be subsonic, regardless what the Mach number on the front end was. That's kind of so I've seen this curve before. Other things that are of interest, we noted that there would always that while total temperature stays the same, total pressure does not, because shock waves are entropic. And in order to satisfy that, the total pressure has to decrease. The stagnation pressure has to decrease. So if you look at the stagnation pressure ratio, P02 over P01, it's this curve here. It's always going to be going down with respect to Mach number. And actually, it tanks pretty dramatically. Which is not that desirable. If you think of it this way, if I have subsonic flow behind a normal shock, right? And I wanted to say that I have so much. I'm going to try to play this game. We'll see if I'm cool enough. I'm going to share my document camera on one side. So if you look up at the document camera, if you look at a normal shock, you have flow going through the normal shock, and it comes out subsonic afterwards. Say that I'm trying to put it through say I'm trying to put that flow through a jet engine or a turbine or something like that. Because when you one place that you might have a normal shock is in the inlet of a jet engine. So your typical jet engine can't deal with supersonic flow. If you look at the first stage of a jet, there's a duct flows coming down this way. You have the first couple stages of your jet engine here, and attached to those are little wings. Those wings turn and accelerate the flow. Actually, more like that. Sorry. Then they change directions on every stage. Sorry. So if these are all just spinning wings, or kind of like a propeller or a rotor, then they can't deal with supersonic flow. And we'll get into why in a minute. So coming into a traditional jet engine, all the flow here must be subsonic, even if you're flying, even if the aircraft is flying above the speed of sound. So, like for your modern jet fighters or whatever, their inlets specifically slow down the flow to be subsonic, and the geometry of the inlets change in order to facilitate that. However, if we lose total pressure going across going across the shock wave, say the shock wave that we had, say a shock wave that's in a jet engine inlet, and our total pressure goes down. If I go over here and look at my wings, so there's my there's an airfoil, have my flow coming in, got some total pressure over here. If we're thinking of this from like an incompressible flow kind of standpoint, then the total pressure equals the static pressure at a point on the airfoil plus the dynamic pressure, right?
Mm-hmm.
So if my total pressure has gone down, what does that mean for the maximum speed that I can attain over that point? What does that mean for the greatest pressure difference I can have across both sides of the airfoil? What happens to that if my total pressure goes down? You can think about it like this too. If I had a higher total pressure, say that this guy here, V1 high, say that that's the same between those two cases, okay? Between these two hypothetical scenarios where one, we have a higher total pressure, one, we have a lower total pressure, okay? Say we have the same, say the flows hit the same velocity in both those cases. What's different about the pressure, the static pressure in each case?
Static pressure is lower when the total pressure is lower.
Right. So, and if the static pressure is lower, it means that I can't make as much lift, right? Because I can't generate as much of a pressure difference across this airfoil. If I can't generate as much lift, this whole thing's not going to be as efficient. This whole engine's not going to be as efficient as it could be. So this is part of why this stagnation pressure drop is not a good deal. And the stagnation pressure drop comes because this is a very strong form of shock wave. So normal shocks aren't all that they're cracked up to be. Not it's not necessarily something that is desirable. Put it that way.
Mm-hmm.
So much for stagnation pressure. Turn this a little bit more because I need to see that. So what else do we see here? If we look at these trends on the slide again, we do see that static pressure jumps right after a shock wave, pretty dramatically too. I mean, if we're traveling at Mach 3, say, up here, it goes up by a factor of 8. It's kind of crazy. Same thing with temperature, and we already saw how temperature can swing even in isentropic flow. When you just throw Mach 2 flow at a wall, it goes up by like 200 Kelvin. Now it's going up by like if we started at 300 Kelvin, now it's like 600, 700, 800 Kelvin. So so the temperature jump's pretty dramatic. We also see a pretty high density jump as well. This last curve down here. So if we want to kind of sum that up, if we're looking at what happens to flow across a normal shock, we're looking at a drop in Mach number and total pressure, but we're looking at an increase in static pressure, static temperature, ambient temperature, and density. I can write those out a little bit. Sweet. So if I'm cool, you can say something like, oh, it won't let me do it. Oh well. I guess I'll just have to write it normally. So if you wrote that out on paper via webcam across a normal shock or across any shock wave, really, we're looking at negative change in Mach number, looking at a drop in total pressure, but we're looking at a gain in static pressure, ambient temperature, and density. So that's kind of a rough summary of what happens when you cross over a shock wave. Now, say that I do that. Say that I go back to my example over here. There we go. All right, so we got a couple of examples of shock waves on this slide here. We got on the left. We got the T38. He created a series of oblique shocks. We have this prototype for the for the Mercury capsule here with a detached bow shock, and we have this airfoil creating all kinds of shock waves going on here. Again, the more solid the line, the stronger the shock wave that it is depicting, or the greater the density change that it's depicting at a given point. Okay, so there we go. So if it's the case, say for this guy here, for the capsule prototype, so if pressure jumps across this shock wave, that means that the pressure right in here is really, 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 really high as compared to out here. So the question is, what's that going to do to drag? There's a sudden pressure if there's a pressure increase right in front of the vehicle.
Then shouldn't the density increase and that makes more drag?
Yes. So yeah, you can think about it in two ways. Because you're kind of thinking about it from like the mathematical definition, I'm guessing.
Of pressure?
Of drag.
Yeah.
Yeah, like 1/2 rho v squared s CD, all that. So yeah, density is going to go up. So with whatever the drag coefficient is, the drag is going to go up. But you can also think about it from like a force balance kind of perspective. And now have more pressure up here, same surface area. So if pressure goes up and surface area is the same, the force goes up too, right? So that means that if we spike the pressure right in front of the vehicle, the drag is going to go up too, because now we have that much more force pressing back on the nose of the in this case the capsule. So we should also expect when we go supersonic and start throwing shock waves around that we're also going to see a massive increase in drag. And this is one of the reasons why say you have a military aircraft, it can fly supersonic, but it can't do it for very long. And that's why that's part of why they intentionally don't do it. They just don't have the fuel to maintain supersonic flight the way that they can maintain subsonic flight. If you look at the difference between like a World War II aircraft, like a B-24 or something like that, it's a subsonic aircraft, right? And they could fly from a location in northern Italy to Romania and back, carrying a full load of bombs and eight crewmen on 4 propeller engines. If you think about the difference in power production between a piston engine of 1940 and a jet engine, an afterburning turbofan of today, it's incredible. I mean, there are turbofan engines out there today that can make an excess of something in excess of 80,000 pounds of thrust. It's crazy, but they burn so much fuel doing it that you can only use all that thrust to be supersonic for something on the order of minutes, not the order of hours. I mean, a B-24's trip would take hours from point A to point B and back. Like it'd be, if I remember correctly, it'd be like a 6+ hour mission. Now you have an F-22 that can stay that if it was afterburning could stay supersonic for only a few minutes. So the sheer difference in drag and the amount of power that you need in order to overcome that drag is crazy when you start going supersonic. So as soon as you go supersonic, you are creating shock waves because you are forcing the flow to turn and get out of your way. So you're going to have to deal with this effect as soon as you enter that region, and it's going to cost you a lot of gas in order to figure out. Okay, but enough of that. Do you have any questions on that?
Nope.
Cool. All right. So along with supersonic stuff, so we talked about flow and all that jazz. But what about ignore the equation on the slide that I'm about to pull up. I just realized that I updated it on my computer, but not here. You can use it, but it's not in its simplest form. Right. So if we look at a pitot tube, I forget. Did I mention these when we were in incompressible flow?
Yeah, it measures total pressure.
Yeah. And if you know total pressure and you know static pressure, you can figure out velocity, right?
Yeah.
Cool. Well, guess what? In supersonic flow, it gets more interesting. So if this was compressible subsonic flow, we still could use the pitot tube to directly measure airspeed, right? We just have to know something about density, which we can figure that out if we know static pressure and temperature, right? So that's not that big of a deal. As soon as you go supersonic, there's a shock wave involved. It's usually a detached bow shock because a pitot tube, I'm going to jump back up to the webcam for a second. Actually, no. We don't need it yet. Let's stay on the slides for as long as we can. Let's stay on the slides. So a pitot tube is kind of like a rounded, blunt shape. So if we think about what happens with rounded, blunt shapes, I mean, back here, we had a very, very sharp guy here with the T38 talon. And you have a very sharp, well-defined attached shockwave here. The more blunt and rounded the shape is, well, the more detached the shockwave gets. And actually, you can see it a little bit more clearly, I think, if we jump back to one of our first slides. So here's that bullet traveling at different speeds. Again, the dark lines are the shock waves forming on it, and the faster we get, we start to get this detached shock wave floating out around front here, and as we go faster, that becomes more defined and much closer to the nose of the bullet itself. The bullet itself, I mean, it's pretty pointed, right? But we kind of see this, but even then, it doesn't come to a perfect point. If you look at a bullet, they're usually at least usually rounded off at the tip because of how they're manufactured and the material that they're manufactured out of. They can't come to a perfect point because the material won't hold it. So as a result, you get this detached shock wave. So same thing for a pitot tube. It's not like a flat plate, sure, but it's not a cone either. So it kind of forces this to detached shock wave. And while it is a detached kind of curving thing, we said that at the center of that shock wave, we can treat it like a normal shock. Why is that? Why can we treat this detached curvy shock wave as a normal shock at its dead center?
I mean, it looks like a normal shock there.
That's more or less it. So let's call it, because like if we look at a dome, say, just a regular like dome, at the very top, there's one point that's perfectly level, right?
Mm-hmm.
Same thing in a bow shock. It has to transition from having a slope going this way to a slope that goes the other way. So at some point in the middle, it has to be perfectly flat relative to the flow. So dead center, where we are expecting the flow to come into the pitot tube, so we can measure its total pressure. It looks like it's going through more or less a normal shock. So we can treat this as flow going through a normal shock and coming into the pitot tube. Awesome. So that also, however, we know that we have a total pressure drop behind a shock wave, right? So that means that the total pressure that I measure isn't the total pressure of the free stream, which is unfortunate. But we do have all these relationships. We have all these equations that we just built up that relate conditions before and after the shock to conditions before to the Mach number before the shock. So let's play with this. All right. So what I want is a relationship between my total pressure behind the shock wave. This is the total pressure measured by the pitot This is, so we want to relate that. We want to relate the static pressure of the free stream, because that's something that I can measure. The flow doesn't have to turn in order for me to measure that. So no shock waves there. We want to relate those two, and we want to do it through some function of my free stream Mach number. Because like that's what I'm ultimately interested in, right? So what I can do is that I don't have an equation for P naught 2 over P1. I just don't. But what I do have an equation for P naught 2 over P2, or the stagnation pressure behind a shock wave, behind the shock wave, to the static pressure behind the shock wave, right? That's like, I can get that from my isentropic flow relations because I'm on one side of the shock wave, right?
Mm-hmm.
I also can figure out my relationship between the static pressure upstream and downstream of the shock wave, because we just worked out an equation for that. Like we have that sitting around somewhere for a normal shock. We just worked our way through it. So if I take those two and I multiply them together, well, downstream static pressures pop out, and I end up with P naught 2 over P naught 1. Awesome, because that's exactly what I'm looking for. So if we work out the math, we get something that looks a bit like this. Rather, you get what's on the slide, but if you substitute in for the downstream Mach number, you get this. Which is called the Rayleigh pitot tube formula. If I could pronounce his name right, that'd be even better, but I don't think it's going to happen today. And that's multiplied by minus gamma plus 2 gamma and 1 squared over gamma plus 1. That's the Rayleigh pitot tube formula. Which seems cool, right? I have a function entirely of the free stream Mach number that gives me my total pressure after the shock divided by my static pressure upstream of the shock. Has all the things that I want in the right place. But what's the problem with this? What am I trying to get out of this pitot tube again? What am I trying to measure with the pitot tube?
Total pressure.
Well, that's what I can measure, but why do I have a pitot tube there in the first place? Why do I care about it?
Measure the velocity, right?
Right. So yes, the pitot tube measures total pressure, but its purpose is to give me a readout of airspeed.
Hmm.
So in this wonderful, lovely expression here, forged from the fires of hard work and shock waves and math, we have. If I'm looking at this and I'm saying I want to know velocity, can I actually get it? Because my velocity is my Mach number, pretty much, and I got Mach number here, up here, and over here. Like, that seems a little problematic. So the downside of the Raleigh pitot tube formula is that yes, it does relate everything together, but it doesn't actually solve for what I want. It's implicit. What you call it? I cannot solve this to be an analytic expression of the free stream Mach number. You cannot do it. So that's unfortunate. but thankfully, you aren't the first ones to have this problem. So when they first started figuring stuff like this out in the 40s and in the 40s and the 50s, they didn't have a computer that you could just chug this equation into and say solve for x, right? So what they did is that they tabulated all their data. So can you see this book?
I can see the book, but I cannot see any of the values on
it. Anybody?
T1 over T or T2 over T1 and blurriness.
Okay. All right. Well, I'll just explain what's here then. So this is this is Appendix B from your textbook.
Okie dokie. That.
Yeah. All right. You have a book too. This works. So this is how you'd figure out normal shock properties and isotropic flow properties back in the day. You'd have someone who went through and worked out the math and created these tables for you to use. And if you couldn't find exactly what you were looking for, say we have like Mach 1 up here, and it's followed by Mach 1.02, and you need Mach 101, you could interpolate between the two points to figure out what you needed. So if you go here, the fifth column over is the sixth column over is P02 over P1. So if I can get a value for that, I can look back over on the far left and get my upstream Mach number. So I can kind of cheat. If I can figure out the if I can measure P02, I can measure my ambient and static pressure. I can compute a number, find it on the table, and find the free stream Mach number that corresponds to it. It's kind of the old school way of doing it. So I don't have to go into Excel and use GoalSeek or something like that, which you can if you want to. But
fun.
It is.
So are like the point or the plus 0, 1, does that mean times 10 to the first?
Oh yes. Sorry about that. Yes.
Right.
Yeah, it's the number on the left times 10 to the positive or negative, whatever.
Okie dokie.
Cool. All right. So much for pitot tubes. Is that book somewhere? Okay. So we'll pop out of here for a second. Any questions on that?
No.
Great. All right. So thus ends normal shocks, or does it? So we're going to move on into the next kind of shock wave that we noticed, or oblique shocks. So as said, with the mercury capsule prototype that we were looking at before. I jump back to slide 20. It's a rounded, blunt shape, creates this detached bow shock. You can treat it as a normal shock right at the center. But away from that, we can't. It's all curved. It's not, rather, to be more general, it's not, the shock wave is no longer perpendicular to the flow. The shock wave is a little bit more well defined for the T38. Back over here, everything's a straight line, and it's attached, which is nice. But again, the flow is no longer perpendicular to the shock wave. So let's try to get a sense of what's going on here before we get too far. So why do shock waves form again in supersonic flow?
Continuity and things like that.
Okay, so you're right. This is what we talked about when we looked at like supersonic nozzles and stuff. But if I have supersonic flow and I stick a potato into the flow, assuming that the potato doesn't instantly like blow apart or vaporize,
Mm-hmm.
why would a shock wave form in front of the potato?
Because it's making the air have to go around it, but because the flow is moving faster than the speed of sound, then it's gonna, achieve the density of whatever the pressure wave that's the speed of sound is. That's what it is doing in front of the potato with a shock wave.
Yeah. You got it. So the flow has to turn around the thing that's in the way. So but because it's going so fast, it doesn't know that it can't hear the pressure wave building up in front of the potato in time to actually turn before it gets there. So eventually this pressure wave just kind of builds up and it coalesces into a shock wave, and that shock wave lets the flow turn. Rather, we could say that the shock wave has to make the flow turn. At least a shock wave that's not a normal shock. You said going through a normal shock, everything's 1D. That means that when we have these curved shocks or angled shocks, the flow's going to have to turn as we go through the shock wave, because that's why the shock wave formed in the first place, to make the flow turn around, because the flow is trying to turn around an object. So as we go through an oblique shock wave, we should expect the flow to change direction. So this also means, if you look at, if we go back to our bullet example, the shape of the shock wave is changing here as I go from, say, Mach 1.04 to Mach 1.3. That means that kind of implies that there's got to be some relationship between speed, geometry, and how much the flow has to turn, right? So that's some stuff that we need to keep in the back of our heads as we go forward. How much the flow has to turn, its turning angle, say, the actual angle of the shock wave and our Mach number are all going to be related to one another. So jump back down. 528. All right, so there's our oblique shock, and we'll start with that as kind of our model for it. There we go. Okay, so if this is our shock wave here, that dark black line, that's going to be our model for the shock. That shock here, we have flow coming into it that's not normal to it, and then it turns, it goes through the shock wave and leaves at some other angle. So that means that we don't just have a component of velocity normal to the shock wave, we have one that's parallel to the shock wave as well. So if we drew that out, it might look something like this. So in a normal shock, flow parallel to the shock wave was 0. Here it is non-zero. We're going to have a look at that. And we're going to try to characterize it using this control volume up here, which I'm going to scribble down quick. and then we'll get back to the document camera and see if we can look at it a little bit closer. Okay, moving back over to the document camera now. All righty. So this is our model. This is our flow domain. We have the shock wave in the middle, and we have flow turning by some angle theta. We have our control volume, which I'm defining as having sides A, B, C, D, E, and F. So we have 3 sides on each side of the shock wave, if will. We have some incoming flow at M1 or some free stream Mach number. We have some flow leaving the shock wave at some Mach number M2. And if I wanted to list, I got pressure, density, temperature, static pressure, blah, 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 for each side. So on and so forth. All right. So how do we deal with this? Well, the shock waves at some angle beta to the horizontal. All right, which is in the same direction as the free stream flow, just so we can reference everything to something. So we need to look at not just one component, but 2 components of velocity. So let's get this game going. One of our favorite games to play is to throw conservation laws at things. So let's throw some conservation laws down and see what happens. All right. So start with conservation of mass. All right, so we got our expression for conservation of mass. Let's see if we can parse this thing again. So, what's this rho v term? What does that kind of remind us of?
Is that momentum?
Momentum, yeah. We got a mass per unit volume times velocity. We know that like mass times velocity is momentum. So this is like momentum per unit volume. Got an S. An S is like an area, right? Cross-sectional area.
Yeah, I get it.
So if I'm thinking of this as like mass flow rate's what? How do I compute mass flow rate?
Velocity multiplied by area.
That's volumetric flow rate.
Multiplied by density.
Right. It's we said way back when that mass flow rate is like rho VA. Well, this actually looks a heck of a lot like rho VA, right? It's rho V, and that's a cross section. That's for cross sectional area. So there's our mass flow rate. Now the integral just goes across a side. It's called all the sides of my control volume and adds up all the rho VAs and sees what the sum of them are. Cool. What about this guy over here, what's this guy measuring? What's rho and v?
Rho v density times volume. That's like the mass change.
Yeah.
And the volume.
Yeah.
Over,
Sorry, go on.
with respect to time with the dt there.
Right. So this is just okay. So we have mass entering and leaving the volume on this side. This is like a flux, if you will. This is just, am I losing mass in the volume? So if we're in steady flow, what happens to this side?
0.
Right, because the derivative of anything with respect to time is 0 in steady flow. So we're left with just this guy here. So let's parse this a little bit more. So by definition, we've constructed B and F up here parallel to the free stream, and C and E parallel to the flow after the shock. So V dot ds, what's that going to be for B and F and E and C? Is it going to be a number or is it going to be 0? What direction does an area vector point? Would be another way of that.
I guess into the area, and it's 0.
Right, because the area vector is always perpendicular to the area that it is associated with. So that would be like the ds vector. That would be like the area vector there. Flows coming in perpendicular to the area vector. So v dot ds is 0 for B, C, F, and E. It only means something for A and D. So if I actually expanded this integral out and I said, okay, so rho 1 times v1, or in this case, in this case, it would only include the horizontal component of velocity, right? Is that a good way to say that? Yeah, it would only be the horizontal component of velocity. So u1 times a1, or the area of side A, that equals, subtract from that, because since the flow is leaving the area at D, rho 2 V2, which V2 really, times 8 times A2 equals 0. That's my integral. As the same as in normal shocks, we define the area on each side of the shock wave where the flow is entering and leaving to be the same. Therefore, rho 1 u1 equals rho 2 u2. Bam. All right, so that's like that was pretty straightforward and actually kind of familiar too, right? Like this is the same result that we got for a normal shock, which makes some sense because we haven't had to care about tangential velocities yet, so that's good. But wait, there's more. So let's do this again, but for conservation of momentum. So look at that. If you look at the conservation of momentum for which called adiabatic, inviscid, steady flow with no body forces, it's something that looks like this. There are a lot of caveats tacked onto that. We'll say that this is just Tangential. All right. So so this is conservation of momentum um, parallel or tangent to the shock wave. All right. Put that in there. All right. So let's parse this guy. So this rho v ds. What do we say that was similar to? What do we say that was?
Mass flow rate.
Yeah. So that's like an m dot. And then it's multiplied by w, which we're calling the velocity parallel to the shock. So that's like mass times velocity, right? Or mass flow rate times velocity. And that is what?
That's definitely momentum. Force.
Yeah. It's a force. It's a change in momentum. And a force is the time rate of change of momentum, according to Newton's second law. Or I can write it as d dt of mv. Normally it comes out as mass times acceleration, but you can just as easily take the derivative of mass instead of velocity. So we got a force over there. Back over here, what's PDS? What does that feel like?
Is that a force also?
Yeah. What's P?
Pressure.
And DS?
That's the differential area.
Yeah, it's or just an area of the side of the control volume, right? So pressure times area, you got force. So except we're saying that this is or hang on, I want to make sure I'm saying this right. Okay. This is the component of that force tangent to the shock wave. All right.
Mm-hmm.
So we're looking at everything as tangent or parallel to the shock wave. So in terms of this, actually let's start with that. In terms of the pressure, if we look at A, so A and D are parallel to the shock wave. Is there any pressure parallel? Is there any pressure or difference from here to here?
I don't think so.
Why?
Because that's along the shock wave, right?
Yeah, and we don't see flow accelerating that way, right?
Mm-hmm.
Therefore, there's no pressure difference. So there's no pressure difference parallel to the boundary, which called parallel to the shock wave for A or D. Therefore, we don't have to worry about those guys. They're all zero. You look at B and F, it's the same pressure on each side, right? Again, otherwise we'd see flow moving through those boundaries, right?
Mm-hmm.
So that means that the pressure on B and the pressure on F have to be the same, and same for C and D. The pressure on those has to be the same. So the integral P ds, looking just tangential to the shock wave, has to be what? If everything's equal and opposite.
Everything's equal and opposite. That's 0, and that's 0.
Yep. Ain't it nice?
Love to see it.
So we got that. Now I just have to integrate this other side. So if we're looking at m dot dotted with the area vector. Sorry, momentum dotted with the area vector. Do we get anything for B, F, E, or C? Is the control, if I'm looking at my velocity vector here, say, is it parallel to the side of B?
I think so.
Yeah, we've defined it like that. In fact, it's parallel on all four sides, B, C, F, and E. If that's true, the area vector at B, C, F, and E is perpendicular to that velocity vector, because an area vector is perpendicular to the side of the thing, right? So the area vector for B is perpendicular to the velocity vector at B, because the velocity vector at B is parallel to that side. So that means that rho v dot ds for B, C, F, and D is equal to what?
0.
0, right. That was easy. However, for A and B, it's not 0, right? Because now we're seeing things that are perpendicular. So let me write this out a little bit larger. So we can do our integral there, and it gets us something like this. That part of which we get. But remember, if we're multiplied by W, or the velocity tangent to the shock wave in state 1 and state 2. And said before, the two areas are the same. So if I go like this, do that. But this is a mass flow rate, right? The rho UA. That's like M. That's like an M dot. What do we know? What do you know about mass flow rate before and after the shock wave? Same or different?
Well, it should be the same, hopefully.
Yes, that means that these guys actually cancel out.
Mm-hmm.
And it gives us the result that the tangential velocity before and after the shock wave are the same. Dun, dun, dun! And the plot thickens. So this is a kind of interesting result. It almost kind of points towards the notion that we might be able to treat an oblique shock like a normal shock, because it doesn't look like the tangential velocity does anything. It stays the same. Nothing happens to it. So we might be able to think about them in at least a little bit similar ways. Oh, wait, there's more. So that was conservation of momentum parallel to the shock. Let's do conservation of momentum perpendicular to the shock, or normal to it. All right, so got our surface integral, rho v ds. Got a u in there, not a w. Again, assuming adiabatic, inviscid, steady flow, and all that fun stuff. All right, so if we work this guy out, we end up getting to, I'm just going to skip ahead a little bit because it's the same process as before. Rho 1, U1, A1. So now it's with the normal component of velocity, or the velocity component normal to the shock wave. Plus rho 2, U2, A2, U2 equals not 0 this time, but it's equal to the pressure difference across the shock, because the pressure on A and D is normal to the shock. It's not tangent to the shock. So now we're accounting for it. All right. So we said before that all these areas are the same, so they all go away. And we're left with something that looks like this. Which should look really stinking familiar, because that is exactly our expression for the conservation of momentum from a normal shock, right?
Mm-hmm.
So that's like a cool thing. It makes sense that we have it. Makes sense that we have it, and it continues to point to this notion that maybe a normal shock and an oblique shock aren't that much different. So let's see what we can pull out of this. Or let's see what we can pull up next. Because wait, there's more. So just to confirm things, let's try to work at this from the conservation of energy and see if we get the same thing there too. So again, assuming adiabatic, inviscid, no body forces, steady flow, our expression for the conservation of energy looks something like this. All right. So, what the heck's this? What's E again? What's this E thing?
Young's modulus.
It was when it was solid. What's this little E? Like a energy thing. Internal energy? Does that ring a bell?
What? Internal energy?
Yeah, internal energy.
Per unit volume?
Per unit volume, you got it. Or unit mass, rather.
Oh, I'm flipping things around.
So anything lowercase is per unit mass. So this is internal energy per unit mass. And that's multiple. That's added with this velocity squared over 2, or if we took this rho into it, it'd be like rho v squared over 2. So what's that analogous to? Ever seen like a 1/2 rho v squared before, or like a 1/2 mv squared?
So that's like the kinetic energy?
Yeah, per unit volume.
Mm-hmm.
Yeah, we'll go with that. It's called, and I pull that row in because it's one just sitting here waiting to be used. So we got our internal energy, we got our kinetic energy, and then and then if you look on the other side, we have kind of like our work terms. So that's like pressure. It's like a force. Force times velocity is power, right? At least when they're all in the same direction. So that's why there's a dot product in there. So we got kind of the internal side and kind of the external side of our conservation of energy. Make sense?
Yeah.
Cool. All right. So if we work this puppy out, again, keeping in mind that velocity is only normal to sides A and D here, so that V dot ds term is going to be 0 on B, C, F, and D again. It's only going to be non-zero on A and D. So if I work this out again, I get something that looks an awful lot like this. And the straight lines around the velocity terms indicate a velocity magnitude, all right? That's like the magnitude of velocity before the shock wave. Rho 1, U1, A1 plus rho 2, U2, A2. Cool. I think that's everything. All right, sweet. So if we take that, crunch it out, remember that all of our areas are the same, collect like terms and all that jazz, and remember that enthalpy is related to internal energy by work. Then we can get, or that rho should probably be a P. Sorry, that's probably, it's called, I think this rho is a P, and that's how we get, enthalpy coming in. Anyhow, regardless, the expression comes out like this. I'll go back and correct that in the online version of the slides. So we get that. So we get that guy. Which should also look somewhat familiar in its final form, which is quite simply when we divide by our continuity equation. So if I divide the left-hand side of this by the left-hand side of our conservation of mass equation, by the right-hand side of our conservation of mass equation, we get the exact same thing that we had for a normal shock. Here we go. Especially because this V1, that's what you call it. If we take the difference out, if we separate this into components U and W, the normal and tangential components of velocity relative to the shock wave, since the tangential components are the same before and after, it ends up just being U1 and U2, which is exactly the same as it was for a normal shock. Bam. So that's conservation of mass, momentum, and energy. We're seeing some pretty intense similarities between what it was for a normal shock and what it is for an oblique shock. The only difference is that there is a tangential velocity. And well, if there are so many similarities, it means that the last thing that we're going to have to think of is, well, if we could just get a Mach number normal to the flow, we could just start throwing our oblique shock relations at this and call it a day. And well, not wrong. So that's our shock wave. That's our velocity normal to it. It's our velocity tangent to it. Then I should also have, then if I have a free stream Mach number, I also could say that I have a component of that free stream Mach number that's perpendicular to the shock wave. So I can define that, Mn1, as the component of velocity perpendicular to the shock wave divided by the speed of sound in the free stream. And I can either find it by finding my components of velocity, or I can just do some trig and say that Mn1 is simply a component of the free stream Mach number that I can find if I know the angle of the shock wave relative to the free stream. Now, if I look at the Mach number behind the shock wave, I have Mn1. By the same token, I can have like Mn2, right? Can Mn2 ever be greater than the speed of sound?
Unless Mn1 is less than the speed of sound, right?
Can Mn1 ever be less than the speed of sound if there's a shock wave?
Then things are going in the opposite direction. But yeah, then 2 has to be less than the speed of sound.
Darn right. However, the tangential velocity we said is going to be the same, but between these two, right? So if I look at this, M1 will be greater than 1. Mn2 cannot be greater than 1. But can M2 possibly be greater than 1?
No.
Well, logically we might think that, but geometrically it might. Because although the flow normal to the shock wave has to slow down, the flow tangent to the shock wave is still going as fast as ever. So depending on how big this tangential component is, we may get a downstream Mach number greater than the speed of sound. we might have flow greater than the speed of sound and downstream Mach number greater than 1. We might. It's possible.
Oh boy.
So this just gets more interesting by the minute. Look at us go. But that's where we're going to wrap it up for today. Do y'all have any questions?
Nope.
All right. Well, in that case, thanks for coming by.